Good morning. My name is Jonathan, and many of you will have noticed that I'm trying to learn your names and not doing very well. Susan is the current record holder. I've asked her name 10 times. I will be helped if you wear a name tag. Many of you are not. And I will be helped if you wear a name tag with your name showing, which is hard to do. A nice thing to do is to get a ballpoint pen and write your name in big, heavy letters on the other side. What I did not work. I wrote my name in such big, heavy letters that I still only have one side working because it ruined the first side. But in any case, you're encouraged to wear your name tag. You're encouraged to have your name tag visible and readable. And you're encouraged to say your name at all opportunities. Virtually all opportunities. So I'm going to talk to you today about statistical philosophy, which many people find to be a funny title. But I believe fairly strongly that statistics is not just a machine you throw your data into and cross your fingers when you're almost done. Statistics is intellectually important, and it's an integral part of science. If you're doing science, you should be thinking about statistics from the beginning. Statistics is the way that we make sense of data and that we understand what our data are telling us. And please put away your big devices, and if you must use your small devices, don't let me or people behind or next to you notice that you're doing that. So my goals for today are to discuss what statistics are used for, why they're needed, to talk and rant about p-values. There's sort of a cult of p-values in many branches of science, and now there's been a pushback against that, and that's all a lot of fun. I'm going to argue that effect sizes and confidence intervals, which measure biological quantities in ways that we can understand, are usually better than p-values. I'm going to talk to you about two basic paradigms of statistical philosophy, so I'm using big words, and I'm going to try to convince you that statistics belongs right in the middle of your scientific practice. About 30 years ago, I was in a hardware store, and they had this little sheet of instructions from a plumbing supply place that was very funny. And it's something that I've never, like everything's on the internet, I've never been able to find this on the internet, but I've tried to construct. There were about 8 or 10 instructions, and most of them didn't show much respect for the intelligence of plumbers, which is interesting because it's from a plumbing supply place. But one of their instructions was any piece of pipe longer than 30 feet should be clearly labeled as long pipe on both ends, and if the pipe is longer than 100 feet, there should be an additional sign in the middle so that the plumber doesn't have to walk all the way to the end of the pipe to figure out if it's a long pipe or not. So this is a long lecture, and I'm giving you the warning at both ends and maybe also in the middle. And try to be patient with me. We might stand up and stretch in the middle. So I'm going to talk to you about statistical inference and what the basic idea of statistics is, what we're using it for. So one attempt that I've had to explain is we use statistics to confirm effects, to estimate parameters, and to predict outcomes. And the example I thought of when I first constructed this lecture, it was my fourth time here teaching something like this, and it was the day after my 5th or 6th rainy Sunday. So here's my example. It usually rains when I'm in Cape Town, but mostly on Sunday. I'm hoping it's going to go back to raining while I'm in Cape Town. This is a little sad now, but anyway, it's the example I have. So I might want to use statistics to ask if it's really true. Does it rain more on Sundays in Cape Town than on other days of the week? Or I might want to estimate. Well, okay, if I've decided it rains more, maybe I'm really interested in how much more it rains. What are the odds? And odds is a technical term that we'll get back to later in the course. But how do the odds of rain on Sunday compare to the odds of rain of other days of the week? And how likely do I think I'm going to get rained on a Sunday while I'm making my plans for next year? That would be predictions. So those are the kind of things. We have some data, we have some observations about rain in Cape Town, and we could ask questions like this. And how we're going to interpret these data necessarily depend on assumptions. You need a philosophy. You need to think about how you're going to think about the data. This is a woman who got caught in the rain in Cape Town a couple years after I stopped giving the lecture. Anyway, started giving the lecture. I haven't yet stopped giving the lecture. So we could ask, for example, if we're frequentists, is it likely that our observations occurred by chance? I had observed 4 or 5 rainy Sundays and 1 or 2 rainy non-Sundays in 4 trips to Cape Town. That seems pretty unlikely to occur by chance. And so we could say, well, okay, I'm convinced. You've shown me that it rains more on Sundays in Cape Town than it doesn't. Or you might choose to bring your prior assumptions. You might say, well, what happened to you is pretty unlikely, but your idea that the weather cares whether it's Sunday or not may be even more unlikely, right? So how many of you believe that it actually rains more in Cape Town on Sundays? Anyone? How many feel pretty sure that the weather doesn't care whether it's Sunday or not? Okay, so some of you are not willing to answer the question or not willing to wake up and listen to the lecture. And I do understand it's been a grueling experience. But we have different philosophies and different approaches to asking questions like this. So this example, and I think all of my examples are based loosely or sometimes not so loosely on real studies. But in every case, the data I'm going to show you is fake data. So I'll just give you that disclaimer in advance. But this is a study where I was not involved in the study, where people, I'm phrasing it hypothetically. Let's imagine a study where we compare health indicators of children who are either treated or not treated with vitamin A supplements, and we might want to estimate things about how these children are growing. So for example, are the children who get the supplements taller or shorter than the treated children? Are we sure that the supplements are helping the children? In this Vitambo study, they found no evidence that the supplements were helping the children. This is from an earlier study. And we might want to know, well, how much is the supplement helping? How much does the supplement cost? Sheetal was talking to you about the importance of prioritization. Once we're convinced it's helping, we still want to know how much it's helping. We want to know how confident we are. Statistics is the thing that helps us take the raw data and try to address questions like this. And I talked earlier about the cult of the p-value. How many of you have heard of p-values? Okay. How many of you have not heard of p-values? How many of you have 1 or more hands? Okay, so there's some people who are just not going to raise their hand. Because really, I have heard of p-values or I have not heard of p-values. And many of you are mathematicians. You should be raising your hand for one of those questions. But I guess there's nothing I can do. I used to take this stick and wave it around, but now I'm on camera, so I'm supposed to stay quietly behind my computer. Quietly may not be exactly the right word. So we use p-values to say how sure we are that we've seen an effect. We use confidence intervals to say what we think is going on, how large the effect is, how confident we are that the effect is that large. P-values are overrated, and I don't say it here, but they're widely misused. Not only do people put more weight on them than they should, but they actually often use them in ways that they absolutely should not use them. And in particular, I'm going to argue strongly, in fact, it's going to be a main theme of the lecture for the next few minutes, you should never use a high p-value as evidence for anything. So people, I guess I'll get to this later, but I feel I should. So you're looking for a low p-value. A low p-value means statistical significance, and the words statistically significant are part of the cult, right? People just say this is statistically significant, this is not, and it's sort of an alternative to thinking about things. And so part of the purpose of this lecture, I guess, is to convince you you need to think about statistics and not treat it as a black box that provides you with simple yes or no answers. So people like to use, if the p-value is low, it means something is going on. Not completely wrong, although overused. If the p-value is high, it means nothing is going on. That is just absolutely wrong. It's not always completely wrong, but you should never use that chain of logic. And why would we want to use a p-value? To show that an effect is small or two quantities is similar. And I'll talk about ways that you can try to show these things, because you might actually want to show these things. You're not allowed to use a high p-value as evidence. And I'm going to give you, hopefully, some convincing examples. That is just a starting, starting announcement of what I'm going to try to convince you. You're not supposed to be convinced yet. That's another part of this talk, right? I'm telling you my statistical philosophy. I want you to listen to it. I want you to think about it, because it's interesting and it's sensible. But I don't want you to adopt all of it. You need your own statistical philosophy. I do want you to adopt this part about not using high p-values, though. So we want to know if vitamin A supplements improve the health of village children. I talked about measuring their height. Is height a good measure of general health? It probably depends on the population. In a population that's on the borderline of being well-nourished, height may well be a good measure of general health. In a very well-nourished population, it may not be a good measure of general health at all. If you're designing, imagine that we're designing this experiment now. You have reason to believe that this group of children might be helped by vitamin A. So we're going to treat some children, we're going to look at them. If we see differences, how are we going to know that the differences are due to our treatment? What steps are we going to take? So those of you, I'm now aware that not everybody in the room has one or more hands, but those of you who do, does anybody have any thoughts about how you would design such an experiment so that you would be able to report, yes, the height differences I see are due to the experimental treatment that I'm giving? What are some basic principles? We have epidemiologists in the room. Thank you.
Randomized.
Wrong.
Sarah.
Thank you.
You can randomize who's receiving the treatment.
Right, so that's the key one. And in some statistical philosophical sense, I'm not getting into deep statistical philosophy. In some statistical philosophical sense, which I'm not going to discuss, that's really what it's all about. Once you randomize, you're on solid ground. We want, in an experiment like this, we would independently randomize each individual to be getting the vitamin A or not. So we first select a group of children. We decide this is the group of children. Here's how we're going to treat them. You decide as much as possible in advance, and then you randomize, right? So you pick at random which children are going to be in treatment 1 and which children are going to be in treatment 2. So if there's any systematic difference between the two groups, it has to be due to your treatment. The only possible sources of difference between your groups should be random, which you can't ever completely avoid, or the thing you want to measure. You don't ever want any other differences between your groups, and certainly not that you can avoid. What are some other things you might do? I don't need to extract these from you, but I actually added them over the years because people bring them up. So if you were constructing this, what else might you do if I'm going to look at the heights of these children after the experiment and see which group is taller, what else might I want to do to make a good experiment?
Kristen, and you need to measure height the same in both groups.
Sure. So you need to do everything carefully and so on. You need to measure height the same. You don't need to, in a deep sense, you don't need to measure height before the experiment. And I've been working with people associated with, I was going to say somebody in this room, but it's actually Roxy and Wim, who are both not in this room. Some people don't measure before the experiment, and technically you don't need to, but it's a very good idea. What you want to do after you randomize, so now all of our sources of error are either random or due to our experiment, the next thing we want to do is minimize the random sources of error to give us a better chance of seeing the non-random sources of error. So we might do things like measuring changes in height from beginning to end of experiment instead of just height. It's not necessary, but you should do it if you're going to bother to do such an experiment, because it's going to enable to see the part you want to see much more clearly. We might want to control for other factors. We might want to see which of these children have heavy worm burdens, for example, and just observe that and use that to take out that source of random error, right? Because there's no systematic difference in worm burden between our two groups because we've randomized the children, but we might want to see our final effect more clearly. Does that Clear? Do people have comments or questions? So what do we hope to learn? We really want to know if vitamin A is good for these children, how sure we are, right? Does it look like it's good? Are we confident it's good? And how good is it, right? Because we want to make decisions based on this study. And how sure are we about how good we think it is? And we can look at these through p-values and confidence intervals, and we're going to see briefly that most of these things look more clear through the lens of confidence intervals, but mostly I'm going to rant to you about p-values. So what does it mean if I find a significant p-value? So I do this experiment, and I'm running my computer, my fingers are crossed, I want p to be less than 0.05, and I just showed the answer, but I'm going to ask you anyway. So if I find a significant p-value, then what does that mean? Kristen again. That's okay. Oh, but you've already heard this lecture.
I haven't.
Well, it's the
But
same.
I
You've heard it somewhere
memorized the
lecture.
definition of a p-value.
Oh, good. No, that's good. So what does it mean?
If the null hypothesis were true, it's the probability of observing a test statistic as large or larger is the one. that you
Yes. Okay, that's a little downstream, but yes, it's the probability. Okay, fine. Not Kristen. How many people have done a statistical test and wished for a low p-value? Okay. What does a low p-value mean to you? Thank you.
That the thing I'm
Wrong.
studying is, Catherine,
Thank you.
that the thing I'm studying is statistically significant. And then we'll have to do other things after that.
Okay, that's kind of a loop. And it's statistically significant. What does that mean? Okay.
I think you can reject the p-value, reject the null hypothesis.
I can reject the null hypothesis, which is that the things are the same. So it means that the two groups are somehow somewhat different. So that's technically correct. That's technically correct. Yours kind of circular, but also technically correct. But so what? I'm absolutely convinced before I even walk in. If I'm giving kids vitamin A is called vitamin A for a reason. It's possible in a particular group of kids it would be bad for them instead of good for them. It's possible that the effect is tiny. It's not possible ever that this null hypothesis was true. Okay? But technically we're all correct. The point of the p-value, the way I calculate the p-value, is I'm constructing the counterfactual, and I'm asking, could the null hypothesis be true in a certain paradigm? But why would I do that? Why would I do that when I absolutely know for a fact that the null hypothesis is not true? And I'm going to say something even stronger. Maybe you don't have the same philosophy of science as I do. Maybe you think the null hypothesis is true sometimes. Maybe vitamin A magically has no effect on this particular group of children, and you need to rule that out. It doesn't matter, because I can construct an example. I can say, okay, maybe the effect is 1 in a million. Maybe the effect is 1 in a billion. Maybe the effect is 1 in a trillion. Your philosophy that there may be an exact zero effect, that's a religion. It has nothing to do with science because it can never be proved. Okay, so we are, on the one hand, we are testing the null hypothesis and rejecting as statisticians in a formal framework. In the other hand, we don't actually care about the null hypothesis for itself because we absolutely know A, that it's not true, and B, that if it were true, we couldn't prove it and it wouldn't matter. Okay, so why do we reject the null hypothesis? What does the p-value tell us as scientists rather than as statisticians? Sorry, what does statistical significance tell us as scientists? So I used to try to extract this answer. I've never succeeded in extracting it directly, but you all kind of know, or most of you kind of know, and I'm going to prove it. Okay, so here are some fake results from this probably real study. So I measured the proportional increase in some reasonable way. I'm comparing now the treatment group to the control group. All my estimates are positive. So forgetting about statistical significance for a minute, I'm happy as a scientist who's trying to give something good to children. So these children have increased weight increase increased fat fold increase, and increased iron level change compared to the control children. Which of these is statistically significant? Raise your hand if you have a hand. Come on, thank you. Okay, hands down. Just wanted to, there are some people that's the first time they raised their hand today. And there's probably some people who still haven't raised their hand today. Does somebody want to, okay, how do I do this? I want to know whether to poll you or just ask you. Which of these is statistically significant? Who wants to tell me? Thank you. Weight is statistically significant? Okay. How many? Okay. That is not correct. So that proves, I guess, that some of you don't, or never mind. What? Okay, sorry. We're going to come back to you. Does anybody have a different guess? There's only 2 left. Yes. Wrong. What's your name? Actually, I shouldn't have said that because you're, sorry? One more time? Okay. Do I know you? No, I'm serious. Okay, it's nice to meet you. Okay. And you said weight? Iron. I'm sorry. So, yes, so you're only wrong for not saying your name. Iron is statistically significant. Why? I mean, it looks to me like there's a pretty big increase in weight, over 1%, an even bigger increase in fat fold. Iron is less than 0.5%. How can you say that's significant?
Because it is the increase, the change in, the increase is little compared to others.
The increase is little, so that makes it significant? Okay. So you're partly right, but I don't think I'm following the whole argument.
We're looking for
Wrong.
Jerry.
Thank you.
The confidence interval doesn't overlap with 0. Doesn't go over 0.
The confidence interval doesn't overlap 0. So even though it's small, you think it's significant because it doesn't overlap 0. And why would that be the significant thing?
We're pretty sure that there's a positive relationship.
Okay, congratulations. You are actually, I think, the first person who ever just came right out and said that clearly, right? So most people know that it's significant if it doesn't overlap 0, but few people are able to verbalize the idea that it's important because not that it's big, right? This does not mean biologically significant. This may well not be biologically significant. This may not matter at all to these children. Statistically significant to a statistician, Shanae and Kristen, means that I've done some counterfactual test and blah, blah. To a scientist, it means I can see something clearly, and typically what I can see clearly is a sign, by which I don't mean I should go now and babble about statistical philosophy. I mean a plus sign or a negative sign, right? So I can see clearly that the effect of vitamin A treatment on iron is positive. The effect of vitamin A on weight and on fat fold might be very large and might be very biologically important, but I'm not seeing clearly that it's positive. So we test the way Shanae tells us to, but the reason we do it is not because we want to know if the effect is 0. The effect isn't 0. We want to know if we're confident that we know whether it's a positive effect or a negative effect. So a high p-value means we can't see something clearly, and a low p-value means we can see something clearly. And that is why I want you to use low p-values sometimes as evidence when there's no better evidence, but I never want you to use a high p-value as evidence. So you're saying is, well, I know this because I can't see it clearly. Or I know this because I can't see something clearly. Never a good line of evidence. Literally never. So here's my visual, right? This is a example where people were not able to see clearly the results of an important American football game. And this is an example of a stunning view of San Francisco where you can see very clearly. And in general, as scientists, p-values are telling us whether we're seeing something clearly. They're not telling us whether something is big or small. They're not telling us whether something is biologically important or not. And they're not telling us anything. I'm going to pick on Catherine with a C if she doesn't mind. They're not telling us anything about the actual sorry, a high p-value doesn't tell you anything about the world. I don't say these two quantities aren't, and for that, aren't significantly different. We say I don't see a significant difference in this experiment. It makes no sense. And you read it all the time in the literature. So-and-so and so-and-so showed that levels of this and levels of this in Botswana, in this population and in that population are not significantly different. That's nonsense. The levels are different. And if you have a different philosophy, you can't win the argument with me. The levels should be assumed to be different. What so-and-so and so-and-so showed was that a particular experiment couldn't see that difference clearly. High p-values mean you don't see something clearly. In almost all simple cases, what you see clearly or not is the sign of some quantity, but eventually we might need to talk about more complicated cases, and that will be fine too. Okay, so, yes?
By that statement...
Wrong.
My name is Ani. By that statement, are you, I guess, saying that whenever there are overlapping confidence intervals, it's just a matter of power of the experiment rather than...
Yes, I personally believe that if you were God and could study not only everything in the world, but possibly everything in a whole bunch of counterfactual worlds, we're talking now about biology and not particle physics, there's always a difference. And as I said, even if you don't believe me, you have to basically follow my philosophy because you're never, ever going to prove me wrong, right?
Jonathan,
yes?
I don't want to interrupt.
Wrong.
Edward, I think it's important to point out that it's possible for confidence intervals...
No, it's not important to point that out.
And the p-value still to be under
Yes.
0.05.
Yeah, that is true. I don't know. I actually decided it wasn't important to point it out, but maybe you're right. What you mean is confidence intervals overlapping 0. Confidence intervals overlapping each other is a fairly subtle point, and we can discuss that later. Thank you, I think. I probably made the wrong call on that. That's okay. So I believe there's always an effect. You can argue with me, but your philosophy must be consistent with the possibility I'm right because you can't prove me wrong. Oh, sorry, I've lost my thread. Kristen.
I don't know if we need to delve into. I was a comment about the ethical, there's an ethical angle to assuming there's no difference when you're designing trials and the fact.
Okay, yes, we should delve into that. Delve into that later. There's a lot of things to discuss. There's a lot to unpack there. And I'm not saying you should never assume that there might be no difference. I apologize. Okay, so having made this bold assertion really challenges the way we think about error, right? Statistics talks about false positives and false negatives. I don't believe in false positives or false negatives. I don't believe in false positives because I think there's always some sort of effect, right? If I'm comparing Botswana to Lesotho, they're never going to be exactly 100% the same. If I'm comparing kids who get vitamin A to those who don't, they're never going to be 100% the same. So I've never made a false positive conclusion in my life because I don't believe there's such a thing as a false positive. And I don't make false negative conclusions anymore because I don't make any negative conclusions anymore. I never say these two things are exactly the same. So these two types of error are not the way we should be thinking as scientists about our data. They are, however, very useful, and I'm going back to Shanae and Catherine with a C. They're very useful in terms of thinking about statistical methods. So the way we think as statisticians and the way we apply statistics to science are different. I'll also mention that I really get fed up. This is not even one of the worst examples. I get, why do we have to know which one is type 1 error and type 2 error? There's perfectly good names. I'll get to you in a second, Rita. Perfectly good names. We're going to call false positive and false negative. And type 3 error is the error of thinking it makes sense to call things type 1 error and type 2 error. Rita. Oh, thank you. And I apologize. The handouts are not up. And I didn't even forget to put them up. I just forgot why it was important to put them up before the lecture instead of after the lecture, so I apologize. But the handouts will be up by 2 o'clock, so anything you miss, unless you're really not understanding right now, I'll just get back to you. But the basic idea is that type 1 error is false positive, and I don't think that the positive is ever false, and type 2 error is false negative, and I never, so, sorry. What? You're still asking?
But like I want to ask something, yes, my question was that you're saying that you never believe that there will be a false positive. I'm not saying that you don't believe that in reality we would reject H naught in the natural sense. It is true.
Right. So H naught is never true, and I never accept it. So I never make a type 1 error or a type 2 error.
Isn't that being biased towards the research? Because you've
No.
already concluded to say that can never happen.
Yes, I think you're going to see. I'm going to come back to your question, because it sounds like I never make any errors, which is obviously false, A, because I'm human, and B, because I'm dealing with real biological data, which is full of noise. So I must make some kind of errors, and we'll come back to my explanation of what kind of errors I make, and then we'll see if you still want to argue with me about it. But first, I'm going to continue apologizing to the statisticians for 1 minute. So if we're trying to design experiments, if we're trying to design statistical methods, false positive and false negative become very useful, because we're living in hypothetical worlds, and we're going to talk to you about designing statistical methods, about simulating data and testing whether you can get your parameters back. And that's all about the old framework, because now we have a hypothetical case that you really know the answers, or maybe you really construct a hypothetical vaccine which absolutely does nothing, because you put it in the computer and the computer says it does nothing. And then we are very interested in false positives and false negatives. And you need to have your false positive rate in this hypothetical world less than your significance value. That's what it means for a statistical method to be valid. And computers really give us exciting opportunities to construct and test statistical methods by this mechanism. And we're interested in false negatives too, right? Before you run $1 million experiment, maybe simulate it in the computer and see if all your assumptions are right, is it likely to work out? And so we could say, what's the probability of failing to find an effect that is there? But very importantly, and this is something many of you have learned already in a very similar context, you can't talk about false negative probability without, as a scientist, making a decision about what you think the hypothetical effect size is. Any method that tries to infer a hypothetical effect size from data or do it indirectly is cheating. You can't talk about false negative rates unless you're willing to say, as a scientist, I want to design this experiment under the assumption that my Ebola vaccine will be 70% effective, or whatever. So false positive and false negative are still very useful before I collect data. After I collect data, though, I have a completely different view of error, which I'm now going to try to sell to Rita. Are there questions here? So the kind of errors I worry about and try to measure and try to, so this is an error I no longer worry about. I was always very bad at baseball, but now I don't have to play anymore. A sign error, right? So I said formally we construct the p-value by thinking about the null hypothesis, but really we use it to see whether we've seen clearly which side of 0 we're on, right? So a sign error is a kind of error I might make, and that's if I think an effect is positive when it's negative or negative with positive. Or a magnitude error. I'm interested in whether effects are small or large, and sometimes, because of randomness in the data, I'm going to make a magnitude error. And so that's how I've recast the way I think about error in the context of actually analyzing the data, but not necessarily in the context of developing my statistical methods. So Rita, you're on the spot.
Okay, like when we consider the false positives and false negatives in the sense that it will help us to understand probably maybe we did the research wrongly. For instance, I'll say if you want to test a certain drug, and then you select people, you put them in different groups, and you give the drugs to this guy and then give them the other group. And ultimately, at the end of the research, you find that you actually rejected H naught and after says it was true.
Yeah.
That can take you back to kind of thinking, maybe probably you selected your sample biasly. So I think the errors kind of in real world research would kind
So,
of take you back?
I would say if I fail to reject H0, and it might not be because I selected my sample badly, if I fail to reject H0, I can't tell whether the treatment helped or hurt. I can't see the sign, okay? And as long as I can see that I can't see the sign, that's fine. I could also see a confidence interval. I mean, it's typically more useful. You learn more from the confidence interval. I've already shown you one example of that than you do from the p-value. But since we live in a world that's dominated by the cult of the p-value, people are also now developing methods to try to put p-values on magnitude, right? So you can define what you mean by a small effect or large effect, and we'll come back to that. But, okay, and I'll talk to you more later if you want to, because I have another question. Correct.
So what could be an analogy for the magnitude error if we compare with the pictures you showed earlier?
So a magnitude error is sort of like a type 2 effect in that if you're going, actually I'm going to get to that. But basically a magnitude error, to be formal about a magnitude error, you have to decide what you mean by small and large. And if you're in a clinical or epidemiological context, you might want to decide that formally before you do the experiment. And so the answer to your question is going to be the flu mask experiment, which is coming up. If your experiment, if the question you're asking is sufficiently simple to be boiled down to one statistic, confidence intervals can be very helpful in clarifying how you think about this. So I'm going to rant a bit more because I have slides with rants on them, but I feel like I've kind of gotten it done. So if I have a low p-value, I see clearly. But it's usually better to focus on what I see than the p-value. And part of the cult of the p-value is you run through the whole thing, and I've seen this happen. You run through the whole thing, you have a significant p-value. This affects that, and you publish a paper. And I've literally talked to senior science, and I said, well, you found a significant effect, but how big is it, and is it likely to be important? And he said to me, well, I never really thought about how big it was biologically, but it's significant. Significance means something, but you're usually better off seeing what you found than how clearly you found it. That should be common sense. High p-value means you don't see something clearly, and the high p-value itself is not evidence for anything, not good evidence for anything. You may not have seen it clearly because the effect is small, or you may not see it clearly even if it's 2,200 kilogram men, because there might be some other reason why you're not seeing clearly. Okay? High p-value should not be used to advance your conclusion. And to just beat this into you, intimidate you from challenging me too much, which is actually not my goal. So high p-values are caused by small differences, and that's what we want to infer. What else causes high p-values? If you have less data, you can get a higher p-value. So if you're trying to show two things are similar, make a smaller experiment, and you're going to succeed. Right? That should scare you. More noise gives you higher p-values. Okay, let's not be so careful about controlling for other sources of error. An inappropriate model can give you higher p-values, and various technical model details can give you higher p-values. High p-value just means you don't see clearly. And a low p-value means your evidence for difference is better, but a high p-value does not mean that your evidence for similarity is better. Could be worse. It depends which of these categories is driving your high p-value. And here is an example that I love, because not only did it happen to me, again, real example, fake data, not only did it happen to me after I met Steve, which is significant, because Steve isn't here. No, significant because I had already started teaching statistics. I'm actually a mathematical biologist. I started teaching statistics about 10 or 15 years ago. But I already started teaching statistics and ranting about p-values, and we submitted this really cool paper, I think, about how many people die of influenza. And it's really hard to figure out how many people are killed by influenza in temperate latitudes because, for a lot of reasons, influenza looks like a lot of different diseases. It can take a long time to kill you. If you have flu, you're more likely to have a heart attack 6 weeks later. And because it's conflated with absolutely everything. It's highly seasonal, right? And everything in the whole world is changing when we're going into the temperate winter. And how do you deconflate all that? And we were the first ones to look at flu deaths not week to week, but year to year. And say in years where it looked like we had a worse flu epidemic, did more people die? And the answer is yes, and I reported things that looked roughly like this. So influenza A seems to be killing people, influenza B seems to be killing people, and cold weather, which is known, by the way, to kill people. When you have a cold snap, people die. You can see it very easily. On an annualized basis, we found it wasn't killing people. And I wrote the paper, submitted the paper, and we had a hypothesis for this surprising result. We said, well, you know, maybe all the people who die in the cold snap would be dead by April, would be dead by the end of the winter anyway. And so when we look on the annualized basis, we don't see it. And one of the reviewers, who I would love to find and give flowers to, wrote back and said it all seemed pretty good, but they didn't understand why we didn't have confidence intervals, right? So what seems reasonable, might as well show the confidence intervals. What do the confidence intervals look like for these values? Is like this, okay? And remember, this is all the same data, it's all the same model. I have no idea. This is what I mean by model resolution. I have no idea why weather had such big confidence intervals, why our model was able to see the effect of flu more clearly than the effect of weather. But to conclude that weather is not killing people on an annualized time scale, it's cold weather is not killing people on an annualized time scale from these data is insane, right? But I made the mistake of thinking that a high p-value was evidence for similarity. It's just not. In fact, given the point estimate, right, I already knew that my point estimate, my best guess for how many people were being killed by cold weather was small. So once I know that, the bigger the p-value, that just means the less clearly I can see it. That means the more noise I have. So this is a perfect example where a big p-value means the opposite of what you think. And I went to all the computers and expunged all of the places where I had made that insane comment about why cold weather isn't killing people, because I have no idea. This study gives us no information about that, and we just say so. So we never say A is significant, in this case flu A is significant, and weather is not significant, so therefore A is more important than B. If we want to say that more people are dying from one cause than another, we have to compare them directly. We have to. And it can be hard, but you either have to do it or you have to just not make statements like that. So stepping back, having a solid statistical philosophy, where does that fit into science? So here's an example of some logic. I don't know why this picture makes people laugh right away. All men are mortal. Jacob Zuma is mortal, and therefore Jacob Zuma is a man. Okay? Is this a true conclusion? Is Jacob Zuma a man? I'm not even getting agreement on that. Okay, this is a true conclusion. How many people think that I've made a solid chain of logic building up to this conclusion? How many people think I have not made a solid chain of logic building up to this conclusion? Okay, some people can't decide. Okay, I'm going to use the same chain of logic, okay? All men are mortal. Fanny the elephant is mortal. Therefore, Fanny the elephant is a man. Okay, nobody would ever say this, right? Because when we're doing science, when we're thinking, when we're making math arguments, we're bringing our common sense and our experience to bear. Nobody will ever say this. People roughly say this all the time, and some of you didn't even notice that this was bad logic because you're driven, you're pulled by the correct conclusion. And that's a really big danger if you don't do statistics carefully. A lot of people are making invalid statistical inferences. They do good experiments that show pretty clearly that something doesn't matter, and then they report a high p-value and they say, we've shown it doesn't matter. Okay, and they're usually right. Why is that important? It's important because it's not advancing science. All you're doing is getting the right answer because you already knew the right answer. In the cases, which are a minority but not a very small minority, where you don't already know the right answer, you're not going to move forward, and if anything, you're likely to reinforce the wrong answer. And there's a lot of this going on. There's a lot of people accidentally, I hope, saying all men are mortal, Jacob Zuma is mortal, therefore Jacob Zuma is a man. And they're usually getting the right answer, but that doesn't make it okay, and don't do it. And we can fix it. In the case of statistical inference, instead of relying on your high p-value, find a way to show it statistically I'm going to give you a more concrete example in a minute. Find a way to show it statistically that doesn't rely on a high p-value. So we can't build statistical confidence that something is small by failing to see it clearly. So how do we build statistical confidence that something is small? We want to see something clearly, but it's not going to be based on the standard null hypothesis. And really, I think this is my answer to Buri, really, we can't even talk about whether something is small. Just like we can't even talk about power. Some of you are familiar with this. We can't even talk about power until we talk about an effect size. We can't talk about whether something is small until we talk about an effect size either. And here's my concrete example. There are respiratory clinics where people wear masks like this because they're trying to protect themselves from certain diseases. It says flu masks here. I don't remember. This is once again fake data based on a real study. But people don't like wearing these masks too much when there's a flu outbreak. They're less comfortable. These masks are more comfortable. And the question is, could we use a simpler mask for a particular purpose? Is it good enough, right? So that seems like a fair thing to test. And here's the words. People who work in respiratory clinics would like to use simpler masks, but they don't want to get nasty respiratory infections. Go figure. So statistically, we're hoping to find evidence that the masks aren't different. Okay, but that's not a thing you can do. And epidemiologists tend not to make this mistake, but if you're talking to an ecologist or an infectious disease modeler or something, sorry, I've jumped ahead. So the way we're going to do it is we're going to use a confidence interval, we're going to decide what we mean by small, and we're going to construct a new kind of p-value. Okay, so what's the old kind of p-value? The old kind of p-value is I want to know if they're different. So first I do a pilot study, a small pilot study. I'm not going to give hundreds and hundreds of nurses inferior masks or different kind of mask before I've given a couple dozen nurses this mask and made sure that they're not all dropping dead. So I do the pilot study, and there's no significant difference. Remember, this is the old paradigm. No significant difference, so I'm pretty happy. And then I do the full study, and still no significant difference. So I can switch masks, I'm happy, right? Maybe. But, you know, it looks a little scary. Like, I'm pretty glad I didn't do a bigger study. Going back time, if it looks to me like if I did a much bigger study, I might have gotten statistical significance, and then the masks would be different. And does that mean I couldn't use them? Does it scare you that I have a model of statistical philosophy where I'm glad I didn't do a big study because then I might have seen something clearly that I didn't want to see? Does it scare you? It scares Kristen. It should scare you, right? We should be able to embrace data. We should be able to do things well. We shouldn't be saying, boy, glad I didn't do a bigger study. Okay, so what did they actually do? What they actually did is before they even started, and by the way, this is another example of my philosophy, we all know that wearing this mask is not exactly the same as wearing this mask, right? Either this mask is a little better or much better. Either this mask is better if people are using it correctly, or people can't stand to use this mask correctly, and in which case this mask is better. It's not the case that the actual difference between these two very different masks is zero. So this is a test of the wrong hypothesis. What did they actually do? They actually, before they even started, they said, well, we're pretty sure, these are trained nurses, we're pretty sure that the better mask is better. We just want to make sure that the new mask isn't worse by a noticeable amount, and we're going to define a noticeable amount, just pull it out of our ears or expert consultation or tradition, whatever. We're going to define it with a number. We're going to say we don't want the new mask to be more than 5% worse. Okay? And now here's the same data, but with the new way of looking at it. And with the new way of looking at it, the pilot study looks pretty good. Looks like it's going to be less than 5% worse. And the full study with more precision actually shows us clearly that the new mask is good enough based on our standard. And I could spend a lot of time talking about examples. I can't believe how long I've spent talking about this stuff already. And if you're dealing with people who believe in the cult of the p-value, you can even attach a p-value to the right statistic, right? So instead of saying, I should have put p-values here on the wrong things, instead of saying, look, 0.3, we win. Now you get to say 0.025, we win, which is obviously a much more satisfying thing to say. The right statistic is a p-value, the right statistic is the thing whose sign we want to know, and the right p-value is a p-value based on the right statistic. But you need to be willing to choose a standard to do it. That took way too long. I'm not even sure what I might skip. There's an exercise which we might have to do quickly or skip or something. But stand up, move your legs, move your arms. Eesh. Okay, I guess I saw somebody running away, so should I pause for 1 minute or should I bold it? I'm going to pause for 1 minute? Okay. So, they say that if you build new highways in certain places, it just brings more cars and you have accomplished nothing. Like making my lectures longer seems to have the same exact effect. I just talk more. Damn it. I like this thing. Okay, so that's the basic philosophy, the idea is my rant against what's wrong with science. What are the philosophical underpinnings? How do we actually do statistics? Shanae already alluded to the main paradigm, which is the frequentist paradigm. So in the frequentist paradigm, it's all based on null models, and it's all based on counterfactuals, right? It's all based on saying, well, what if this were true? What would happen, and how do I use that as a way to make inferences about the real world? So we make a null model, and we say, if we falsely assume the null model is true, what is the probability the effect we see could be due to chance? So in my vitamin A experiment, the difference in proportional growth between my treatment group grew more than my control group, and they grew more by some small amount, 0.0048. So I want to know if that could happen by chance. Well, what would happen if I tried to calculate the probability of getting exactly this value? Before I did the experiment, if I said, what's the probability that I'm going to see a difference of 0.0048? Would that be a high probability or a low probability? Jeremy can't decide whether to yawn or raise his hand.
I think it would be very low or zero.
It would be low or zero, depending on my philosophy of discrete probability distributions. But that's obviously not how I see whether the effect could be due to chance. Does anybody know how we deal with this problem? How do frequentists say or define the probability that an effect could be due to chance? You can't just ask the question directly like you might like to. So what do you do? Yo.
Alan, we look at whether the difference is equal to or greater than.
You look at whether the difference is greater than or equal to. So what's the probability that I saw an effect that large or larger? And there's a whole debate, which I actually can also get very excited about how you deal with two-tailed models. And I'll just say briefly, what I do is I'm not going to say briefly what I do. I need to figure out how to get through my lectures. So this probability, somehow suitably defined, is the p-value. And if something couldn't easily have happened by chance in the null model, then we reject the null model. And we've talked about that's not really why we do it as scientists, but as a statistical paradigm for how to decide whether you've seen a sign clearly. It makes perfect sense. And here is an example. Here is the actual fake data from my experiment. And the average in the treatment A people. Can somebody tell me what these colors are quickly? I'm not joking. Red and blue? Yeah. Thank you. I would have guessed green and purple, and I usually do pretty well in colors, but apparently not always. So the red people got the treatment. The blue people did not get the treatment. The red people have a slightly higher mean proportional growth. So this is probably the best statistic to use, and that's another digression. But we measured the children, we measured them again, we saw how much taller they were, we calculate it as the log of the ratio. They grew more, but could this have happened by chance? I don't know. The simplest way to conceptualize this in the null hypothesis, under the null model, the red children and the blue children are the same. My null model, which I'm perfectly happy to adopt as a counterfactual, Rita, is that these children are absolutely the same. And I can simulate, I have a computer. I can simulate this null model directly. I can say, well, if the red children and blue children were the same, any red child, any blue child might as well have been any blue child or red child. And I can say, well, let's do the experiment again. Let's assume that I randomized them again. It doesn't matter at all whether I gave them vitamin A or not. And here's a new perfectly valid experiment in my null world. And here's another perfectly valid experiment. And here's another perfectly valid experiment. And here's another one which is a little scary. I just did these at random this morning. Here's another one which is a little scary because this is a way the experiment could have come out in a hypothetical null world, and you would be scared to death if your experiment happened to come out this way because it looks like vitamin A is stunting these children. But it's not. It's just a random rearrangement of the same children, as you can hopefully see better than me because of the clear blue and red labeling. And what you do is you do this approximately 2,000 times. You say, if the null model were true, this is the range of differences I would get. And then you say, well, what is the difference I did get? And does it look unusual? That's the fundamental paradigm of frequentist statistics. We imagine that there's no difference. We construct a world where there's no difference, and we compare our real statistic to the distribution of statistics. How many people have done a permutation test like this? How many people have done a t-test? Why do you do t-tests instead of permutation tests? This is a trick question, although you're welcome to try to answer it. The reason we do t-tests instead of permutation, no, not only is it a trick question, I asked it backwards. Why is the t-test the thing we know how to do? It's because Gauss and Fisher and the people who invented statistics didn't have computers. That's really the only reason. This is the basic fundamental frequentist thing to do. All that weird normal distribution t-statistic stuff literally was only invented when it was invented because they didn't have computers. It does have advantages. It's a very powerful framework, and I love it. But this is the basic rock-solid stuff. You can just simulate your null hypothesis and see what would happen. And that's all I'm going to say about the frequentist paradigm, apparently. Yes?
Sorry, could you please, Jeanette, could you please interpret for us what that graph means?
Yes, thank you so much. So what I've done is I've taken each of these. I did this 2,000 times. Not this. I did this 2,000 times. And each time I look at the difference between how much the one group grew and the other group grew. And so each of those, this is now a histogram of my 2,000 points, right? And so the one where it looked like vitamin A was killing everyone is probably down here or even down here. Sorry, stunting everyone. And I just do it 2,000 times, and I see what would happen under the null hypothesis. And I ask whether what I've seen is unusual under the null hypothesis. And by the way, I'm so glad you asked me this question because I skipped this completely. It's not, right? This looks like it's well within what could have happened by random chance. And what does that mean? Does that mean that the vitamin A miraculously evaporated when I gave it to these children and had no effect on them whatsoever? No. Does it mean the vitamin A didn't help these children? No, it probably did help these children. It kind of looks like it helped these children. It means we're not confident whether it helped these children or not, which is exactly the same as, who said it for me? I can't remember. I think Jeremy. It's exactly the same as saying our confidence interval, if we made one, which I'm not going to talk about right now. Steve's going to talk about it soon. Our confidence interval, if we made one, would contain 0. We're pretty sure it affected the children. It's more likely it helped them than hurt them, but we're not sure. Thank you so much. I sometimes get carried away with myself.
I'm just so confused about about the graph.
And are you still Catherine?
Yes, I am still Catherine.
And you're still confused about this?
The previous one, because, and it may be something that you're unable to see, why the colors, why there's red and green and blue.
Oh, because
In
what?
both sides.
I'm sorry. I said that too fast. What I've done is I've redone the experiment, and I've put the children, I've re-randomized the children into A and B, but I haven't changed their colors because I want you to see which children they are. Yes. Yeah, so the children who are green stay green, but I counterfactually redo the experiment and put them in group B. Yes, and I said green, didn't I? Like, I think I said green multiple times. No, I'm actually colorblind. You don't need to be polite about that. I've come to terms with it. Okay, fair enough. More questions? Yo.
I'm looking at the communication trends.
Yeah.
I'm liking it. I'm thinking, so which one is better? Us sticking to the t-test and the t-test?
They're both better. I mean, they're both better, and if you have a specific question, I'll be happy to discuss it. I'm using the permutation test because it's the clearest way to understand the philosophy. The t-test has the same philosophy, and it's almost as solid, and it can be more powerful, but it's harder to explain in a 5-minute lecture, right? I mean, here we really understand what frequentist philosophy is about. But they're probably both better for your application. Yes?
Kristen, have you ever had issues with using permutation tests in papers issues getting them accepted?
No.
No.
But, you know, I'm good at bluffing. Yeah?
Alan, so the permutation test, you take the observations you observe and scramble them and do them
Yeah.
times. Whereas in a t-test, where you simulate that, you would get observations that you observed and new observations at each simulation. Like you'd be sampling from the distribution. So do you lose anything by only, I mean, is there a difference in the test characteristics across?
Yeah, so what you lose, and it's not very important, and I'm going to make this the last question about that. You can find me later. What you lose is actually on the t-test side. The t-test, the reason you do it like that is you've had to assume a normal distribution, and you may or may not assume equal variances or things about variances. So that's the difference. It usually doesn't matter, but if anything, the permutation test is a little more solid. So no more questions about t-tests, but we can have more questions about frequentist paradigm. Okay, so the other paradigm, which is not the frequentist paradigm, is the Bayesian paradigm. And the Bayesian paradigm is pretty different. Frequentist paradigm, we boil things down. We say, if things were really simple, what would happen? Now what really happened? How does it look? So assumptions are simple. Conclusions are a little bit weird, right? In the Bayesian paradigm, we make a complete model world. This is a complete model world. It's a model of the city of Shanghai and an exhibition center. And once we make a complete model world, we can ask questions about probability. Instead of saying, does my confidence interval contain 0, which is a little confusing, I can say, what's the probability that vitamin A helped these children rather than hurt them? What's the probability that it helped them by an amount of more than 10% on my scale? So the Bayesian framework gives us more power, and with great power comes great responsibility. You have to make all these assumptions, and you have to make them carefully because your results now depend on assumptions. So I don't know how many of you are familiar with the Spider-Man tagline, with great power comes great responsibility. So with Bayesian interval, we need a statistical model of how our data are generated. So we need to assume things like normal distributions. And we need to take that to a probability model of parameter values, which requires prior distributions. We have to say, well, the probability that the effect of vitamin A is going to be a certain value has a certain distribution. So Bayesian inference requires explicit assumptions about everything. And the advantage, again, is it gives you great power. So just briefly, a comparison. As a frequentist, I know exactly what to do with data like this. It's simple, it's clear, it's reliable, it's close enough to write. I don't have to make any assumptions at all, except the counterfactual assumption that the red and blue were drawn from the same population. As a Bayesian, I would need to say, well, what are the possible effects of vitamin A? What do I think it's likely to be? Do I want to use what I think it's likely to be, or do I want to use something more broad-minded and less biased? A Bayesian trying to analyze data as simple as this will drive you crazy. They'll try to make uninformative assumptions and let the data drive the model, but a frequentist has no such problems. There's also advantages. So in my mind, this is a clear example where you're better off being a frequentist. And I'm hoping that most of us are going to develop pragmatic statistical philosophies, which means we're frequentists when that's the easier, better thing to do in service of science, and we can be Bayesians when that's the better thing to do. So for the Cape Town weather, it's easier to think about as a Bayesian. It would be very hard, assuming that somebody could get you to engage with the question of whether it rains more on Sunday or not at all. It would be very hard for a frequentist to put everything into that model, whereas a Bayesian would just say, well, I have lots of prior reasons for thinking that it's super unlikely that the weather knows whether it's Sunday or not, and you could either formally or informally construct a Bayesian argument that just rejects all this nonsense fairly easily, right? Because it starts from saying, well, I already believe it's super unlikely. A Bayesian has no problem saying, I already believe it's super unlikely that the weather knows whether it's Sunday or not. Or you may disagree. You might be a Bayesian who thinks that the weather doesn't like me and rains on me on Sundays after I spend my whole week teaching. Okay, so here's an example, and I am going to try to do it quickly. I did warn you it's a long lecture. So we're going to have about 4 minutes for this, and this is an example that really shows the mechanics of how Bayes' theorem and the calculations we make as Bayesians work. So MMEV, I should be warning you about this as well from a public health point of view. It's a viral infection that causes a serious disease called MMED, and patients with MMED are unable to control their urge to fit models to data, and you guys are actually a higher than average risk group. So a certain population has a prevalence of 1%, and we have a rapid test for MME virus, gives a 100% sensitivity. So if you have MME, another thing, we should have better words than sensitivity and specificity, just like we should have better words than type 1 and type 2. Gives a positive result 100% of the time if you have the virus, 5% if you don't have the virus, okay? So I'm now going to ask you, get a pencil, a paper, and a friend. I pick a person from this population at random. I test them with the rapid test. The test is positive. A person is selected randomly. Their test is positive. What's the probability they have MMEV? A person is selected randomly. And I apologize. I should have one slide with both of these sets of information. There. I shouldn't have said show off. Does anybody think they have the answer and wish to share? So you can say the same thing in such a positive or negative way. So what do? Well, we pick somebody randomly from the population. There are 4 things that can happen, right? They could be positive and get a positive test. They could be positive and get a negative test, which actually is not anything that can happen, and so on. And so we can write down the probabilities of these 4 things. If we're being careful, we can multiply them out and ask if they add to 1. And if we did it right, they should. Okay, that's our model world. So what's the Bayesian step? This is what Bayesian calculation is we observe how much we can learn from what we've seen. So this is before we did the experiment. Now we've done the experiment. We've tested the person, and they're positive, right? So these 2 things didn't happen, and one of these 2 things did happen. So we calculate our new probability by adding up all the things that might have happened and renormalizing, right? So the probability that I was positive and had a positive test is 0.01. The probability that I need to renormalize it, the probability that I had a positive test at all, right? All the different things that are competing is 0.01 plus 0.0495, which looks to me like 20 over 119. Did anybody get 20 over 119? Yes? Okay, so it might be right. Which is some number of percent. Did anybody get a percent? So the probability that they have MMEV is, I didn't write it, and I don't know it. Nobody did it? Okay. Anyway, it's approximately 1/6. Let's say it's 17%. Okay. So that's surprising, right? This is a better test than any real test, right? It gets it right 99% of the time if you're negative, 100% of the time if you're positive, and yet still the probability that somebody is MMEV after they have a positive test is only 17%, which is really not part of the theme of this lecture, but it's kind of interesting, right? And the reason is because the relative, 95%. Basically, you're 20 times more likely to get a positive test if you have the disease, right? 5% is 1 over 20. But you're about 100 times more likely to not have the disease in the first place if you're chosen at random from the population. So basically the 100 effect, the fact that the disease is rare, is actually a larger effect than the strength of the test. So that's interesting in a whole nother dimension, which I don't want to get trapped in. But I do want to get trapped a little bit by this question. Okay, you learn that a friend of yours has had a positive test for MMEV. What do you tell them? This is a trick question. It's a great way to elicit answers is by telling people it's a trick question. But if I don't tell people it's a trick question, I feel guilty when they don't get the right answer. You learn that your friend has MMEV. Wrong. Mulalo.
Yeah, maybe
You're supposed to say your name.
That 17% of the chances that the results may be true. The test may be true.
Right. So that's the trick answer, right? You learn that your friend has MMEV. You tell them, well, you need a follow-up test, but has a positive test. Well, you should get the follow-up test because I'm being responsible. I'm not a doctor. But you probably don't have MMEV. Okay. So that's a perfectly reasonable answer, except for Mulalo's refusal to say his name. You are Mulalo, yeah?
Yeah.
Okay. Fine. Yes?
I'm really lost.
Why are you lost?
I think it goes back to the table.
Yeah.
I don't understand how you calculated the 20 over.
Okay. Oh, how I calculated 20 over 119? You're not supposed to understand. Sorry. I did the math too fast in my head. So you as long as you can get to here, you're good. How did I get to here? Okay. That's a good question. Sorry, your other question I would have pretended was a good question, but this one's really a good question. So I asked, what are the 4 things that could have happened, right? Positive, 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 negative, and so on, yeah? So, and I did that by multiplying. If I'm positive, I have a 100% chance of a positive test and so on. Is that part clear?
Okay, so
If I'm positive, I have a probability. So I pick somebody at random. They're either positive or negative. These are the probabilities. Then I give them the test. What am I doing wrong? Oh, I'm so sorry. So I pick someone at random. So it's either 1% of being here or 99% of being here, right? Once I pick them, I give them the test. If they're positive, there's a 100% chance that they wind up in this box, yeah? If they're negative, there's a 5% chance they wind up in this box, they get a positive test, and a 95% chance they get a negative test. Right? So those are the things that can happen and their 4 probabilities.
Okay, so the probability, if you're positive, if you actually have the disease and you test positive, is what times what?
You can't read it. It's 0.01, which is the probability that you were positive in the first place, times 1, which is the probability of you getting a positive test. Here it's 0.99, which is the probability you had in the first place, times 0.05, which is the probability of getting a positive test given that you're negative. Here it's 0.99 times 0.95. Okay. And then, that was meant to be the easy part. The hard part is that you then cross this out. Once I observe the positive test, I know it's not a negative test. These are the possibilities that are left. Thank you. And your name is? Thank you. So, why is Mulalo not giving me the right answer? What's the difference? What's the fundamental and sort of Bayesian difference between these two questions?
Charlie, maybe you should tell your friend to get another test to be more sure.
Well, yes, absolutely. And I completely agree, and I kind of claim I already said that. But that's not the actual difference. Julie doesn't like the way I'm asking the question.
No, I know where I was just going to help.
Okay.
It's one, which is by saying that, well, actually, all of my friends have an uncontrollable urge to fit models to data, and therefore, I think that my friends have a really high preference that I mean,
Fair enough. Yeah. I didn't even think of that aspect of it. I didn't even think of that aspect of it. Yeah, okay, so I'm just going to go ahead. The answer, the difference between these two questions is here I told you why the person had a test. This person had a test because I picked them at random. Why did your friend have a test for MMEV? Did anybody test you for hepatitis C in the last month? If you learned your friend had a test for hepatitis C, would you go look up the sensitivity and specificity and do a thing like this? The first thing you want to know, and which I was trying to leave out of the equation, is who are your friends? Because they're already not random. But in a more general case, if I hadn't had such a silly example, the first thing you want to know in this case is why was your friend tested for MMEV, right? And as a Bayesian, you want to be explicit about everything. Here I explicitly said they're chosen at random. I know why they were tested. I know this calculation is correct. Before I think about this question, I need to think, well, what are my assumptions? And I need to ask, why was my friend given a rapid test for MMEV? Was there a crazy math biologist just roaming the streets, grabbing people and forcing them to take MMEV tests? Or is there something I don't know? Okay, so in conclusion, statistics are not a magic machine. If you're trying to do math, particularly if you're trying to do science, you're not allowed to just treat it as a black box at the end. You need your own philosophy of science. I think it should resemble mine because I happen to think I'm smart, and also because I've been thinking hard about statistics for the last 10 years, but it should really be yours. I think it should be pragmatic. You don't want to be somebody who believes in Bayesianism or frequentism as a religion. They're tools that you use, but they're tools that you use by understanding them. And be honest, which is the hardest part. And is John here? John took me on this. It's hard because you look at your data, you find things that you think are true, and the tendency is to confirm them without necessarily being careful. And again, you're usually going to be right, but it's harder than it sounds. There's a lot of subfields which have a culture that you do an experiment and then you insist on finding a significant result there. And that really subverts the whole philosophy of statistics. I've already talked enough about confirmation bias. I'm trying to do this. I'm not even good at it yet, but you people are young and maybe more impressionable. What you're supposed to do is keep a data analysis journal. The first thing you do, even if the second thing you do is look at your data instead of make a plan, the first thing you do is open a data analysis journal. What am I looking at? What am I exploring? How much have I probed, and therefore how much can I trust my results? And I'm going to post actually some links about this now that I think about it. Okay, so it's been a long lecture, and we're going to have a long summary. Sorry, maybe you saw this slide and thought we were done. So be honest. Oh, didn't I just say this? Oh, I went the wrong direction. So in summary, p-values are overrated. Never, ever, ever use high p-value as evidence for anything ever. And people always say to me, well, look, in this context, it's indirect evidence that my effect really is small. Fine, great, congratulations, you have indirect evidence. Now go away, find the direct evidence and show it to me. Seriously. use effect sizes in confidence intervals when you can, and you're just going to dodge a whole bunch of these problems without even having to worry about them. Otherwise, you figure out how to make significant p-values do the work that needs to be done. And we've talked about some of the ways to do that. Frequentist statistics makes weak assumptions, finds at least formally logically weak conclusions that sound something like this. The parameters are unlikely to produce a statistic this extreme by chance, therefore I'm fairly confident I know the sign of the parameter. Bayesian statistics make strong assumptions. We fully specify our prior distributions, and if we believe our strong assumptions, we find logically strong formal conclusions. The probability that the effect values in this range is X, and that's particularly useful for prediction. If I'm studying the Ebola epidemic right now and I want to know what I think is going to happen next week with proper amounts of uncertainty reflecting both my fit and all the craziness that my fit thinks is going on in the world, Bayesian tools are really good for that. Statistics are a key component of database science. You should be thinking, if you're collecting data, you should be thinking about statistics from the beginning. Do not attempt to tack it on at the end. You need a basic understanding of the principles. You need your own philosophy. And if you're a scientist, it should be pragmatic and honest. That's the end of the talk, but I still have one more slide because I get pushback on this last one. So what do you mean if I'm a scientist? If I'm not a scientist, should it not be pragmatic and honest? And the answer is not necessarily. So if you're a theoretician, then you probably have an ideological, but hopefully honest view. And there are people who get into Bayesianism and frequentism as religions. Bayesians are offended by the way frequentists use counterfactuals, and frequentists are offended by the fact that Bayesians try to assign probabilities to things that aren't, in some fundamental sense, probabilistic. If you are a capitalist, your philosophy of statistics should probably be pragmatic and dishonest, right? Gets you the answers you want. And we all know the hardest job is politician, because a politician needs to be ideological and still manage to be dishonest.